Okay, guys, so the first question for kinetics and equilibrium, this is a pretty involved question. I'm going to give you an example of a reaction, and then we'll just go through all the things that could stress it out, and which way the reaction will shift and what happens after that. So let's do, we'll call it Le Chatelier's principle. And it talks about how a reaction that's in equilibrium will shift to try to get back to equilibrium when it's stressed out. So for temperature and concentration, so if I change the temperature of the reaction, or I add substances or take away substances from the reaction, you can use up and away, down and towards, the trick to help you figure out which way it's going to shift. That's an O. Okay, so let's do this reaction. I have N2 plus H2. These are both gases, and I'm making 2NH3 gas plus energy. And to make sure this is balanced, we need 3 there. Okay. So the question will tell you what the stress is. So let's say, I'm going to do this in a different color so that you can see it. Let's say the stress is temperature, and they're saying that they increase the temperature. You want to find the thing in the reaction that could represent temperature. In this reaction, it's energy. Sometimes there'll be a number there instead, like an amount of kilojoules. So whether it says the word energy or it gives a number of heat, you can use that as your temperature. Okay, I'm going to get rid of that number now just so that you're not confused. Okay, so if I'm increasing temperature, I want to find temperature in the reaction, and I want to put an up arrow above it. If I was decreasing temperature, I would put a down arrow. So whatever the question says you're doing. Now I want to follow up and away, down and towards. If the stress is facing in the upward direction, remember equilibrium is always a double arrow. I want to think about which of one of those arrows is facing away from the blue arrow I just drew. So if I want to find the one that's facing away, it would be the one going to the left. So I'm shifting left. If my reaction or my stress said that I was decreasing temperature, then I would want to do the down and towards trick. So which of these 2 arrows is facing towards the arrow I just drew? The one that's going to the right. So now the other thing they can ask you is what happens to concentration after the shift. So if I'm going to the right, the amount of NH3 would increase because it's on the right side. The amount of N2 and H2 would decrease because it's on the left side. So whatever side you're going to goes up. Okay. Oh, I'm going crazy over here. Okay. So guys, the same thing is with concentration. They're going to give you something specific and say that they either increased it or decreased it. So let's say the stress is that I increased the amount of H2. I would find H2, put an up arrow above it, and then I would want to figure out which of these arrows is facing away from that. If I'm going away from the arrow I just drew, that means I need to be going to the right. If I'm shifting to the right, the amount of NH3 increases because it's on the right, and the amount of N2H2 decreases because it's on the left. Okay. If the substance was going down, you would put a down arrow above it, and then your equilibrium would want to face towards it. So it's the same exact thing, temperature and concentration. Pressure is where things get a little funny because you need to pay attention to what phase the reactants and products are. Pressure only affects gases. So if you see anything in the reaction that's a liquid or a solid or aqueous even, you want to totally ignore it. So what you want to do is you want to count up the number of gases on each side. So for this reaction here, I have 1 nitrogen and 3 hydrogens. That's 4 gases on this side, and I have 2 gases on this side. So whichever side has the most gas has the most pressure. So this left side has more pressure, this right side has less pressure. Now, equilibrium wants to be reached again after a reaction is stressed out. So whatever the stress is, the shift wants to fix it. It wants to do the opposite of it. So let's say I increase pressure. The reaction wants to decrease pressure. So which way is it going to go? It's going to go to the right. If I decreased pressure, that would be a stress. The reaction would want to make the pressure go back up. So which way would it go? It would go to the left. And again, we'll write it down just so that you have it like as a note. Whatever side you go to, increases, and the other side decreases. Okay? All right. How can I tell if something has reached equilibrium? Okay, so I want to talk about these 2 words, rate and concentration. So they're either going to ask you about the rate of the forward and the reverse reaction or the concentrations of the reactants and the products. And if the question says equilibrium, you always need to say that the rates are equal. As products form, there are other products turning back into reactants, and that happens at an equal rate. If they ask you about concentration, the concentration on both sides stay constant. So that's the wording you would look for to know if something has reached equilibrium. Okay. Leo asked about a PE diagram, so that's question number 3. I'm going to draw one for you. They look like this. So this right here is the activation energy. It's how much energy you have to add to get a reaction going. If you add a catalyst, this bump literally gets lower. So we lower the activation energy. And other wording you can see is alternate pathway. So you like line the molecules up so that when they collide, it's going to be a perfect collision, even if they don't have a ton of energy. Okay, so that's what a catalyst does, and that both of those things increase the rate, so they both make the reaction go faster. Okay, how are kinetics and equilibrium related? So I'm not sure. I feel like they don't necessarily have to be in the same unit. Kinetics is the study of reactions and how they happen. So kinetics includes collision theory, when we talked about how the molecules have to collide with a lot of energy and at the perfect angle in order to react, and then all the things that we can do to make them react faster. And then equilibrium talks about when you have a forward and reverse reaction that are going at equal rates, and then if you stress out that reaction, you're kind of like changing the number of collisions, and you're causing the reaction to go one way or the other a little bit faster. So I guess that's why they're kind of stuck in the same unit, because once a reaction is stressed out, we go back to thinking about collisions to figure out how it's going to fix itself, what's going to happen and how it's going to fix itself. Okay. Okay, acids and bases. This is a pretty, I'm going to do this right on this page. Arrhenius acid. You want to look for something that makes hydrogen ions or hydronium ions in solution. That's a fancy way of saying it. An easy way to pick out an Arrhenius acid is that it has an H in the front of the molecule. So anything with an H in front, you can say is an Arrhenius acid. I would never guess. I would always check table K first. Table K has a whole list of acids. If something's on that table, it's definitely an acid, and then you don't have to worry about remembering definitions. How do we know it's a base? It releases hydroxide ions in solution, which is a fancy way of saying that it's ionic and ends in OH. So these are some examples of bases. And again, guys, I would always check table L, which is a list of common bases. And if it's on that list, it's definitely a base, and you don't have to worry about thinking about it. For litmus paper, you want to look for it turning red. That's going to tell you that it's an acid, versus blue. If litmus paper turns blue, that's going to tell you it's a base. Okay. For this last slide, I'm going to do one extra video just because I think it's going to be a little bit long. Okay. See you guys soon.